separating variables. Kathleen, when you're done, let me know. Done? Did you solve for y? It doesn't look like you solved. You said separate. No, I said solve by separating variables. All right, the way you want to see it written. If you write it weird, you may not. All right, so what are we at? Let's see. I need to put my y over here. How many dragged my k with me, with my y? You drag your k with you, you're making it more complex. Leave the k where it is fine, over there with the t. Okay? So here we go, here we go. What do we have? Jacqueline, what's my next step? Okay. Me. K squared. K is a constant. I'm just kidding. Is the derivative of the KK? Okay, I know, but if this is the antiderivative, so KT plus C, okay? All right, lots of random variables going on here. K and C are both constants, keep that in mind, okay? So now what? We're going to solve for y, Megan. Sure. Okay. All right. Now remember, when we did this before, we separated it out. So it's got to the point where we didn't need that. We just made that a K. Okay, well that would be awkward since we already have a K. So here's what we're going to associate. This is going to be y sub 0, and it should look like an exponential growth and decay thing. Does it? Looks slightly familiar, I hope. So this right here is the same as dy dt equals k y, right? That's where we started all this. Okay? Now, the pre-cal, we already started with this. Okay? So calculus may start with this, but you can slowly, if you don't want to do all that, you know this is equal to this. Y sub 0 is just that initial value. That's what we called it. We called it that when we did the other day. I know initial value means what we start with usually, but it doesn't have to be. It can just be what we know. Yes. Yes, it is. Initial condition, or they call that in physics.
So yep. You do the C instead of K.
Yes. And you'll get used to that because you'll be starting at the same point. All right, and then there you have it. K is your relative growth rate. Okay? That is not your rate of growth. That's something different. But we'll get into that when we get into that. So, if you see this, know that it's the same as this. You can work it out, or you can just jump right to there because you know. Let me show you an example. Okay. Again, I could have gotten this out of your pre-cal book. Okay. The scientists observed 125 bacterial colonies growing in the agar of a petri dish. 6 hours later, the number of colonies has grown to 190. All right. We're going to construct a mathematical model, which is just an equation. Okay, that describes the number of bacterial colonies present T hours after the start of the experiment, assuming exponential growth. Okay, so if we're assuming exponential growth, what's our starting point? Y equals y sub 0 e to the kt. Okay? This is exponential growth or decay, whatever the case may be. Okay, in this case, we're growing. All right. So what's the 125? Y sub 0. Because that's the beginning of our experiment, so that's going to go right there. Okay? What is the 6? T. Good. E to the k times 6. And what's the 190? That's the y of, in this case, 6. Okay? All right. Now, basically, we have to find k. Yes, ma'am?
So is that a cruise equation that we did here at the beginning? Is that what we'll start with right now?
If you're assuming, yes, exponential growth or decay, yes, that's your starting point. Yep. Okay, so go ahead, solve. Let's not round.
We're solving for C.
Yes, we got to find k. Because that's in our mathematical model here. Okay. What do we do now to solve for k up there in that parenthesis or exponent?
Change the equation to ln of 190 divided by 25, because you're dividing 125 from both sides, equals 6k.
Okay.
And then you can divide 6 out of that to get k alone.
Okay.
And then solve.
All right. So this is k ln 152 over 6. All right. So our mathematical model is y equals, what was our y sub 0, 125? E to the k t. Okay? Now, I'm okay with this. Yes, you have an E and you have an ln, so it could be simplified, but I'm really okay with that. Let me show you how that would work. In case it's a multiple choice question, they probably wouldn't give that to you because that's not simplified. So this is a 1/6, right? ln 1.52, 1/6 is the same as that over 6, right? Okay. Remember, if we want the E and the ln to cancel out, they got to be right next to each other. So where does this go? Exponent, good job. 1.52 to the 1/6 power. Okay, now we cancel. The 152 jumps down, and we have 1/6, and don't forget there was a t there too. So this is technically simplified. If you're a multiple choice, that would be probably how it looks. That's 1/6t, but this is really fine with our purposes. It's not multiple choice. It's for your response. Okay? No, because then you have to round it. Okay. I don't really want you rounding way this early in the problem. Okay, good question. What? Yeah, there's a B, a C, and a D, I believe. That's A. All right, so here's B. Approximately how many bacterial colonies will be present exactly 1 day after the experiment begins? Okay, I'm going to go on double page here so we know y equals 125 e to the ln 1.52 over 6t. And what's t? 124. Which one?
24 because we were using 6 hours.
That's right. We're using hours. So 1 day is 24 hours. Okay, so this is a simple little problem. We have to just solve 1.52 over 6 times 24. Now, if you want, and you will want probably to do this, why don't you go ahead and store your K? Remember how to do that? ln 1.52 over 6. Okay, I got it. STO. Okay, I'm going to store it as a K. Alpha K is the parentheses. Okay? Now that's the stored answer. That's not the abbreviated answer that you're even seeing up there. That's the stored exact ln. Okay. So 125 e to the k times 24. Oops, don't need parentheses. There you have it.
If we had it stored the K, would we multiply the exponent by 24 because 24 or 6 divided by 24 is 20?
And then you do 4 ln of 1.52. Yep, that would have been the same. For every problem, yes. So what's my answer? 667. Was that the first integer?
Yep.
Okay. That's vector colonies. Kind of try to get in the habit of thinking about units, because some of you all would have made a unit mistake there by putting 1 in instead of 1 day. You were talking about 1 hour. Okay. All right. Assuming that resources are not a limiting issue to growth. Remember that petri dish is eventually going to get kind of full, and then it's like not going to grow. But we're assuming that's not an issue. Okay? That's what that means. How many hours will it take the total bacteria population to reach 20,000? Yeah. So that seems like it's a ways off. So what's the 20,000?
The Y.
The Y. So we're going to put Y equals, I'm going to start back up to 125 e to the, I'm going to put a K like that I remember I have K in my calculator, where I put the quotes on it. And I'm going to put 20 right here, and I'm going to solve it. Okay? Now you're solving for T. And we're down to the nearest hours. Took us 24 hours. It took us from 125 to 667. So,
Did you say rows in your
yes. Add it now to your calculation. Yeah, it's right in. Oh, yeah, and I have it. I don't know. All right. I'm going to divide my 125 out next. And then I'm going to, and you can simplify this or you can leave it. It's not going to hurt anything. ln on both sides. So whatever this is divided by k, and you should get approximately 73 hours. Did anybody not get that? I did. It's right here. I just didn't show it. Did you not get 73? When you get to, this is your problem. Did you get to this point, Megan?
Yeah, I had 160 equals 125 e to that
160, no, it's 20,000.
20,000 divided by 1.
It is 160, okay? So then what do you get? What did you do after that?
And I made it ln of 1.52.
It should be ln of 160 equals kt. This is the ln of 1.52 is already taken care of by our k. Where are you getting that? put your K in there. Yes, and then put it down here. Because that's KT, e to the KT. Okay, that's all for K, for T. Knowing you got K. That's why I use the quotes, because that reminds me that I got K. I don't have two variables there. Okay? All right, so mathematical model, you need to find K. That's the number one step. Pretty much always on these kind of problems. Okay. Half-life problems are always exponential decay. Y'all remember the half-life problems? Okay, we're constructing a function. Find K. That's the only thing missing on your function. Okay, y equals y sub 0 e to the kt. Okay. What about the c?
You say so it's thank you for the line C.
Well, that's the same as y sub 0.
Oh, right.
Yeah. All right. Okay. What do I know? I got one number, 5730. Where does it go? 5,730 years to take it from full to half of what we have. T, that's right. So T is 5730. We don't have K. E, all right. What the heck are we doing? We're missing y and y sub 0?
It says the initial mass.
Yeah, but we're not there yet. I mean, we don't have a number, right? We don't have a number to use. What are we going to use? Half-life, what does that mean?
So 1/2 y equals 1/2 of y.
Okay. So throw some numbers in there.
Okay, so y is 100. Then y is 15.
Okay. Regardless of what numbers you did, you're going to get to this point, correct? I would just start there. And I wouldn't even do the 1 here, but let's see. Okay? E to the K times. So, but you got to understand what half-life means. Whatever you started with, you're going to have half. If you start with 100, it's going to put you down to 50 in that time frame. Start with 1, it's going to put you down to half in that time frame. Okay, go ahead and find your K. If you do this a few thousand times, you'll be like, okay, I'm there. So that's where I'm cutting to the chase here. That's what I got, but I'm not rounding. Careful, watch the whole problem here. Okay, did you all get that? Negative 1.29, 209, blah, 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 times 10 to the negative fourth. Okay,
The units of that.
all right, be careful, don't lose that. All right, so we're looking for a function. Okay, so y equals, just put a 1 there, because it doesn't matter. It may matter later, but it doesn't matter now. E to the, what was it, ln 0.5 over 5730 times t. There's your function. Y0 is not defined here, so we can just throw whatever we want. I probably should say not defined, not designated. Honestly, it wouldn't be wrong if it makes you kind of crazy, just put something in there, just put that in there. Okay? If you want to put just y sub 0, since they really didn't give us anything. Okay? But you'll have to use 1.5 or, 150 Any questions on that function? Okay,
I don't understand.
what?
I don't understand.
Half-life is if you found something that, a fossil of some sort, and the scientist said, oh yeah, it's supposed to last this long, but it was this, then there's a formula that how long it lasts. There's a number of years for how long half of it will be still there. That's what half-life is. Like say you're supposed to live till you're 90, according to your doctor right now, you'd be 45.
It's used with
Because that's how they figure out how old things are, by their half-life. How long it takes them to totally decay to nothing.
It's used for carbon. Yeah, it's mostly for.
Yes, I mean, all right. This is the same problem. I mean, part B of the same problem. Given 300 grams of C14, what is the remaining mass of the isotope after 250 years having elapsed? Okay, so here I'm going to go. I know my K is negative because it's a decay, right? Okay, that's why it's negative. Where does the 300 go? Iso 0. E to the K, we're going to store that, and time is 250. Now you don't really need to store it this time because it'll be just easy to grab it. I get the last thing I did, so now I'm going to take 300, E to the, I'm going to grab that answer, times 250. Okay, you just cut and paste, it'll pop back where you are wanting. Sometimes it acts weird, you want to store it, that's fine. So we should have 291.6. Okay.
Oh, 3 grams.
All right, thanks so much.